In this lab, we are demonstrating the effects of not having a net force of 0 on the motion of an object using Newton's second law, thus implying that the velocity is not constant in this case. Based on these parameters, we'll be comparing two computational models with an observed one. One model will only have gravity force interacting with the object, and one model with both gravity and drag force. Two formulas that will aid us in this are derived from Newton's second law. The velocity update formula being velocity final equal velocity initial plus net force divided by mass times delta t, and the position update formula being position final equal position initial plus delta velocity times delta t. We are interested in knowing this because on a bigger scale where we are not able to observe in person, we should be able to predict the position knowing the surroundings impact on an object. Now that we know the problem and the reason why we are interested, let's get started. Let's take a look at an observational video I recorded myself of an object falling from a certain height. In this video, the object is an empty wallet, and the reason I used an empty one is because I wanted to get my object to get the most interactions it could with the drag force. And the lighter an object is, the greater effect it has. The object is falling from the height of 1.778 meters in the negative y direction. The time interval is 0.017 seconds, and these are the measurements I got from the video. Observed time being 0 to 0.402 seconds, initial position being negative 0.281 meters, initial velocity being negative 0.288 meters per second. As you see in the graph to the right, it's curved, which indicates that the object was not in a constant velocity and had other forces interacting with it. To compare this data, we'll take a look at two computational models. This is the code I used to predict the future position of my object with the changing velocity, based on Newton's second law. To get started, I used the initial data from the observed video, the initial position, the initial velocity, and the time interval for this simulation. I set the delta t to be very small because the smaller the timestamp, the more accurate data you can predict. The mass was 0.1748 and the gravity being 9.8. Two main formulas we're using to calculate the position is the velocity and the position update formula based on Newton's second law. One thing that differs for the two computational model is the net force. Since gravity 1 only has gravity affecting it, the net force formula is F net equal to the gravity, and gravity being the object's mass times the gravity times -1 unit vector for the negative direction. For the model with drag, the F net equal gravity plus drag. The gravity formula being the same, but the extra is the drag formula, which is B, the proportional constant for the magnitude of drag force, times the object velocity squared times the positive unit vector since it's opposing the gravity force. Let's take a look at the program's diagram. This model is a good representation of Newton's second law because this code uses the laws and its principles to clearly predict the future positions, given all the forces and initial measurements. As you can see, the one on the left is with gravity force and the one on the right is with gravity and drag. The graphs show a clear difference between the lines as in the initial look. The change in the two models seems to match the differences that should be seen when using the law, as the one with drag should be more leaning towards a linear line. Let's take a look at all the models compared to each other. The red line is the model with gravity, the blue line is with gravity and drag, and the orange line that can barely be seen is observed. Initially, all of the models are at the same position, but as time passes, the gravity one is steeper and it predicts the position to be further than it actually is. However, the model with drag is almost perfectly aligned with the observed. This makes sense, since in the real world, when an object is dropped, it will have more forces interacting than just gravity. Since we are calculating the forces that is going against the gravity, we get better reading as it is more accurate to real world. The gravity-only model is better suited for predicting motion on a planet with no other forces than the planets. In the beginning, there were few discrepancies because the object was falling, it was flopping around, and the wallet was opening up, which was causing the velocity and the movement to be off. To better get more accurate readings in the future, it would be best to tape the wallet shut so it doesn't flop around. To end this report, let's answer the big conceptual questions. Number 1. The model that would best predict terminal velocity would be the one with drag. However, in order to get the terminal velocity, we would have to let the object drop for longer, as we would need the two opposing forces, gravity and drag, to cancel each other to get net force of 0. Since terminal velocity is reached when the net force is 0, it would mean that it is also the constant velocity. Number 2. There would be no difference in terminal velocity. You throw it down initially, all it would do is have a greater starting velocity, but it would eventually begin to slow down and reach its terminal velocity as the two forces start to even out. So in conclusion, either throwing it or dropping would have the same terminal velocity but have different initial velocity.